Today, I'd like to talk about a certain class of numbers from combinatorics called law numbers. So let's jump right into the definition. So the n-kth law number, which we'll denote by LNK, is the number of ways to partition the set 1 to n into k ordered subsets. So let's look at some examples. So L31 is equal to 6. And so remember, for L31, we want to partition 1 to 3 into one ordered subset. And so, well, that means we've got 6 possibilities. Like I said before, we've got 1, 2, 3. So we'll have that be our ordering for this subset. 1, 3, 2, 2, 1, 3, and so on and so forth. Notice that that's simply the number of permutations of the set 1, 2, 3. And I think you can pretty quickly argue that Ln1 is simply n factorial. Now let's look at L32. So that's going to be equal to 6. And we can count those pretty easily as well. And that's because if you've got a partition of 1 to 3 with 2 subsets, one of those subsets has to be a singleton, and then the other one has to have 2 elements. And so here on this line, I've got the subsets or the partitions where 1 is the singleton, and then we've got 2 possibilities, 2, 3, or 3, 2. Remember, they have to be ordered. Now here, I've got the line where 2 is the singleton, and then finally down here is the line where 3 is the singleton. So now let's calculate L42. So that's the number of ways of partitioning 1, 2, 3, 4 into 2 ordered subsets. And so here we have 2 possibilities. What I'll call type 1 plus 3, in other words, a singleton, and then a 3-element subset, and then type 2 plus 2. So let's count these up. So if you've got type 1 plus 3, you know you've got a singleton. I'll call that singleton A. And then you've got a 3-element subset B, C, D. Okay, nice. And now, how could we count this up? Well, how many possibilities are there for this A? Well, there are exactly 4 possibilities because we've got 1, 2, 3, 4. So we'll start with 4. And then after that, there are 3 numbers left over that we can permute any way that we want. And that will make the ordered subset with 3 elements. And so how many ways can we permute the 3 remaining? Well, it's exactly 3 factorial. So here our possibilities are 4 times 3 factorial, in other words, 24. Now let's look at type 2 plus 2. And so in this case, you'll have 2 2-element subsets that are ordered. So I'll call them A, B, and C, D. But notice that we might as well assume that this first subset contains the number 1. But the 1 could be right here, or the 1 could be in the second element. So I'll outline both of those. So here we could have B, and then comma 1, and then C, D. Okay, cool. Now let's count up how many possibilities this gives us. And so here we've got a 1, and then there will be 3 choices for B. And then, well, the elements in here in this next ordered portion of the partition will be made up of 2 elements that are fixed, but they could be in either order. So that gives us 2 possibilities. So in other words, we've got 3 choices here, 2 possibilities as permutations. In other words, we have 3 times 2 possibilities of this type. And similarly, we have 3 times 2 possibilities of this type. So in the end, we've got 6 for each of those. 24 plus 6 is 36. So that means that L42 is equal to 36. So now what I'd like to do is build a recursion of these law numbers, or for these law numbers, and use that to build something called an exponential generating function, which we will in turn use to get a closed form. Thanks for sticking around this long into the video. If you're enjoying the video, make sure to give it a thumbs up. And if you're not yet subscribed, think about subscribing. It really helps us out. Okay, so now let's build this recursion. So we'll start with Ln plus 1k. Let's recall that that's going to be the number of ways to partition 1, 2, 3, up to n plus 1 into k ordered subsets. Now we could break those partitions into two pieces. The first piece is the number of partitions where n plus 1 is a singleton. So of course, if we're looking at all of these partitions into ordered subsets, some of them will have n plus 1 as a singleton. And it turns out that if n plus 1 is a singleton, it's pretty easy to count up how many possibilities there are. And that will be Ln, comma, k minus 1. Well, and why is that? Well, n plus 1 is a singleton. We're left with 1 to n. But then n plus 1 is taking up its own set, which means we're left with k minus 1 total sets. Okay, so that's the first part of our recursion. Now, the second part will be the number of partitions where n plus 1 is not a singleton. And here's the way to think about that. Well, we can build a partition of 1 to n with k ordered subsets into a partition of 1 to n plus 1 into k ordered subsets. And that will depend on where we place n plus 1. So let's say down here, we've got a partition of the set 1 to n into k ordered subsets. And I'm going to write it like this. So it's going to start at A1, for instance, and end at A sub I1. So I'll just put A sub I1, I sub 1, meaning that it's the first of the ordered subsets. And then it'll start at, well, I'm just going to put an A star here. That's just going to be some index, probably one more than this AI1. And then it's going to end here at A sub I2. And then we're going to continue that. And our last set will end at A sub IK. So there we've got our K ordered subsets. And this is going to be a partition of 1 to n. And now I'd like to observe that there are going to be n places to put the number n plus 1 before one of these numbers aj, but in the same set. So the important thing here is it's in the same set. So for instance, n plus 1 could be placed right here before a1, or it could be placed right there before a2, or it could be before a sub I1. It could be before this AI star or this A star, or before this AI2, so on and so forth. And I think it's pretty clear that there are n choices there because that's before any of the numbers from 1 to n. Remember, all of the numbers from 1 to n are on that list. But notice that leaves out a couple of places, or I guess I should say k, places where we could place n plus 1, and that's at the end of this set. That's why I put here before aj, but in the same set. And so that leads us to our second possibility, and that would be k places to put n plus 1 at the end of a set. So that would be slotted right here at the end of the first set, slotted right here at the end of the second set, so on and so forth, slotted right here at the end of the kth set. So altogether, there are n plus k places that we could stick n plus 1. So here we've got n plus k, but then that's going to be multiplied into the number of partitions of 1 to n into k ordered subsets, but that's exactly the n-kth law number. So now let's bring this down right here. We have Ln plus 1 comma k is equal to Ln k minus 1 plus n plus k Ln k, and that is our recursion. Okay, so now let's get to using that recursion to find something called an exponential generating function. Okay, so we just determined this nice recursion on our law numbers, and now I'm going to introduce this exponential generating function. So I'll abuse notation a little bit, but I've got L sub k of x is equal to the sum as n is bigger than or equal to k of 1 over n factorial Ln k x to the n. So this is the exponential generating function for, the n input where k has been fixed. So I'll let you think about what type of generating function we could build if we wanted to be a two variable type of generating function, but we're not going to do that here. Now, I'd like to point out that n must be bigger than or equal to k, and that's because if k is larger than n, then lnk is necessarily 0 because that's partitioning 1 to n into more subsets than we have elements. Okay, nice. And I guess I should say I don't have the word non-empty here, but I think that's implicitly understood. Okay, so whenever we're dealing with exponential generating functions, you often build a differential equation. That's why we have this n factorial here. It works nicely with taking the derivative. So that's exactly what we're going to do. So let's find this derivative. So I'll write it as L prime sub k of x, but just term by term differentiation gives us the sum as n is bigger than or equal to k of 1 over n minus 1 factorial L n comma k, and then we've got x to the n minus 1. Notice the n comes down here and cancels that n factorial to an n minus 1 factorial. Okay, so now what we'll do is do a re-indexing. I'm going to replace all my n's with n plus 1s, and let's see. That'll give me this sum as n is bigger than or equal to k minus 1, because from our re-indexing, we have n plus 1 bigger than or equal to k, which means n is bigger than or equal to k minus 1. Okay, and then we've got 1 over n factorial, and then now we'll have ln plus 1 comma k, and then we've got x to the n, which is nice because now we can apply our recursions. So let's just bring some of this stuff down. So we'll have 1 over n factorial, and then I'm going to apply our recursion, perhaps, let's see, into two sums. So that means I'm going to apply the recursion and split it up into two sums kind of immediately. So we'll have ln k minus 1 x to the n. That'll be from our first term. And then we'll have plus the sum of n plus k. And I lied, I'm going to split it up into three terms. So I'll have n over n factorial, and then ln k x to the n, and then plus this sum of k, and I can bring the k out front, and then 1 over n factorial, lnk, and then we have x to the n. And here we have n bigger than or equal to k in these last two sums, because if n is equal to k minus 1, lnk is going to be 0. Okay, so now I'm going to do a bit of simplification. Just as before, I can take this and turn it into 1 over n minus 1. And then I can also subtract 1 from that x and bring an x out front. And now I'd like to observe that each three of these are kind of a nice form of something we've already seen. So let's observe that this first one is L sub k minus 1 of x, just by our definition down here where k is replaced with k minus 1. And then this second one is simply the derivative that we've already seen. So we've got x times this derivative L prime sub k of x. And then this last one is simply k times L sub k of x. Is that right? Yeah, that looks good. So now what we can do is observe we've got a first order linear differential equation. So let's move some things around to put it like in a nice form. So we'll have 1 minus x times L prime sub k of x, and then plus k L sub k of x, or I guess I should say that should be minus, equals L k minus 1 of x. And like I said, we have a first order linear differential equation. The standard strategy for solving these kind of things is to find an integrating factor, which isn't so hard in this case. We'll just multiply both sides of this equation by x to the k minus 1. So that'll give me 1 minus x to the k here. We've got this L prime type term minus k times 1 minus x to the k minus 1, this lk term, and then 1 minus x to the k minus 1, lk minus 1 of x. And then the important thing to notice is that we've just taken this left-hand side and written it as a derivative of a product of functions, it's pretty easy to see that this is the derivative of 1 minus x to the k times L sub k of x. Okay, so now let's bring this line up to the top and see what we can do with it. Now, before we move on, I'd like to tell you about my second channel, Math Major, which has full courses in mostly upper division math classes. And I keep that ad-free thanks to support from channel members and patrons. If you'd like to help me keep this channel ad-free, think about joining the channel membership or the Patreon. But of course, there's no pressure to do this. Enjoy the videos as you wish. And so let's get into it. So we ended with this derivative with respect to x of 1 minus x to the k L sub k equals 1 minus x to the k minus 1 times L k minus 1. And what I'd like to start with here is taking the second derivative, or actually taking another derivative. So take the derivative of this equation we have right here. So that turns this first derivative into a second derivative and deposits us with a first derivative in this right-hand side. But I'd like to observe that I can use this line right above on that first derivative of the right-hand side and rewrite it as 1 minus x to the k minus 2 L k minus 2 of x. So that motivates us to take derivatives over here on this left-hand side until we hit the kth derivative. So now I've got the kth derivative with respect to x of Lkx times 1 minus x to the k is equal to L0x. I think it's pretty clear that that's how that would descend over there on the right-hand side. But L0x is going to be the exponential generating function for partitions of the empty set. Of course, there's only one of those, and that's when there are exactly 0 subsets. And I think in that case, we would just take this to be equal to 1. Now what we'll do is take the antiderivative of both sides, k times. So that's going to give us or leave us with 1 minus x to the k, Lkx equals x to the k over k factorial. That's the result after taking the antiderivative of the number 1, k times, plus a sub k minus 1, x to the k minus 1, up to, let's see, a1x plus a0. Of course, we get those terms because their kth derivative is all zeros. That being said, it's pretty easy to see with like initial conditions and such that all of these terms are 0. So we can just set that equal to 0. And another way of seeing it is that the lowest power of x in this L sub k of x is x to the k. But that means the lowest power of x in this left-hand side is also x to the k, which means the lowest power of x on the right-hand side is x to k, but then we have it. But now let's observe we've got Lkx is equal to x to the k over k factorial times 1 over 1 minus x to the k. So there's our closed form for our generating function, which we'll now use to find a closed form for the law numbers. So this is what we were just deposited with. We've got our generating function could be expressed in terms of law numbers over here, and it's got a closed form over there on the right-hand side. Now, let's expand that closed form on the right-hand side using the binomial formula where our exponent is minus k. So that's going to give us the sum as m is bigger than or equal to 0 of, we've got x to the k over k factorial. And then after that, we're going to have minus k choose m. Well, I'm actually going to put a minus 1 to the m in here first because we've got a minus 1 attached to the x. And then we've got minus k choose m, x to the m. So we're left with something like that. But now let's move some things around and then expand out that binomial. So we've got the sum as m is bigger than or equal to 0. We've got a 1 over k factorial, and then we'll have a minus 1 to the m, and then we've got minus k, minus 1, all the way down to minus k minus m plus 1 over m factorial times x to the m plus k. Now, let's talk our way through that. This binomial coefficient will be a descending product of m terms starting at minus k. So that's exactly what we have in the numerator over m factorial. But now I'd like to observe, I can take this minus 1 to the m and negate all of these. So, or make all of them positive. So notice we've got k times k plus 1 all the way up to m plus k minus 1. But let's see. That's going to allow us to rewrite this thing as m plus k minus 1, choose k minus 1. Maybe it might be most natural to write this as m plus k minus 1, choose m, but that's going to be the same thing as m plus k minus 1, choose k factorial by some obvious binomial coefficient identities. Okay, so we've got something like that now. And now I'm going to re-index this thing, and then I'll be home free. So what I'll do is I'll take m plus k, and I'll set that equal to n. In other words, I'm maybe setting m equal to n minus k, I guess you would have. So let's see. That means we're going to have the sum as n is bigger than or equal to k of 1 over k factorial. And then we'll have n minus 1, choose k minus 1, x to the n. But check it out. Now we've got a series in n with a variable x to the n over here on the left-hand side and the right-hand side. But that means that the coefficients have to be the same. So we've got this 1 over n factorial, ln k, has to be the same as this 1 over k factorial, n minus 1, choose k minus 1. In other words, after moving some things around, we have our nk law number is equal to, let's see, it's going to be n factorial over k factorial, and then the binomial coefficient n minus 1, choose k minus 1. And that's a good place to stop.